Port to cloud. Okay. Did you all just get a message that the recording, that this is being recorded?
Yes.
Okay, very good then. All right, so welcome to the What's a Microcontroller with Python and the Microbit workshop. And it's not really day 3, it's day 1. And my name is Andy Lindsay, and I'll be your main presenter. Aristides Alvarez will be co-hosting, though currently Stephanie Lindsay is responding to your chats and will bring things to my attention if she thinks that it's a good question for everybody else to hear the answer to as well. So today we are going to be talking about the kit that you received in the mail, which when put together, it's going to look somewhat like what you see here on the left. And we will actually be taking some voltage measurements of the kit, of circuits that we build on the kit, and probably of this first circuit that you see right here. By the end of Friday, we'll also be taking some more in-depth measurements of things that circuits do, similar to what you see here on the oscilloscope screen on the right side. And along the way, we'll be talking about the curriculum that accompanies this kit, the lessons, how to implement them. We'll have lots of questions and answers about, hey, I'm working with this kind of class, what would you recommend? And I may be asking you some things as well about, hey, I'm documenting it this way. What do you think about that? So with that said, this is, I just wanted to stop and talk about some things that are causing this more in-depth look at electronics to happen. So many of you may be familiar with receiving a bag of electronic parts, but there's become quite the large amount of material where you follow the instructions to put the circuit together and make it go. And we've gotten somewhat away from the how and the why of that, and also somewhat away from the math. And because of the fact that we sensed a void there, Parallax, in conjunction with cyber.org, said, okay, how about if we fill that void? How about if we make something available that actually takes a deeper look at electricity and electronics using the same familiar parts, but gives people the opportunity to take measurements on their circuits, to do some calculations and match it to what they measure. And part of the reason that there's a couple of reasons for that. Cyber.org is an NSF funded organization, and they have two main interests. One is cybersecurity and cybersecurity awareness, and then the other is workforce development. And so we have two things going on that you may have been hearing in the news lately. One is the reshoring of a certain amount of manufacturing and technology. And if that continues, which I'm pretty convinced it will, we really need to train workforce to be able to go into those positions and to have some interest in them. Additionally, workforce is all the more important because if you've been hearing in the news lately, places are having quite a bit of difficulty finding employees who are ready to work and ready to do the jobs needed. So those two things make what we're looking at today and on Wednesday and Friday particularly relevant. And I need to mention cyber.org underwrote part of the development of this program. So we thank them very much for that. And I hope you all will agree with me after this workshop that it was a worthwhile investment on their part. Okay, so Today, we're mid-overview, and so after doing the overview, there was some pre-workshop homework that went out. We'll do some questions and answers about that, and after that, we'll set up our breadboard kit and talk about continuity, which is basically an electrical connection, and how that happens on a breadboard and how to measure it. It's something that students will get to possibly have a more hands-on approach than they've had previously, unless they're in a full electronics workshop with lots of expensive equipment. So what we'll be doing is causing the microbit to be some of that expensive equipment for them. We will also build and measure a first circuit, and then we'll have some homework for you to build up some more circuits to be ready for Wednesday. Now, on Wednesday, we will be working with lights and push buttons and talking about a list of concepts that those are used to introduce. And it's probably a more robust list than we usually see when we're talking just about lights and push buttons. Between Wednesday and Friday, we'll have you connect a servo and a potentiometer, which is kind of a knob that you can twist to cause electrical changes to happen in a circuit that get measured, and we'll be able to use that to do some interesting things, controlling the servo and light blinking speed and some other things. So on Friday, we will work with the servo and the potentiometer. We'll talk about upcoming activities, do a tour of the available teaching materials, both provided by Parallax and provided by cyber.org. It's the kind of thing where you can mix and match depending on what you need for your class. We'll also be talking about some of the neighboring kits, such as the Cyberbot robot, which is also a microbit, a device that has a microbit brain. And we'll talk a little bit about simulation, which is something that I have yet to add into these lessons. And so I'll show you what I have so far. So here is the kit that we'll be working with. In the middle here is the Microbit Go bundle. And then starting from the left, we have, or bottom left, let's do we have a longer cable in the kit, because this one is going to be kind of difficult for students if they've got the breadboard set up sitting on a table and they want to be working on it while they're connected to their computer. Certainly this is okay for a laptop, but especially if you have desktop computers, the longer cable is going to be important. We have some Alligator cables which support microbit documented activities, but we also use a couple of them as probes for taking measurements on our setup. A servo motor. This black thing on the top is the adapter, so you can plug the microbit into one end and then it goes on the breadboard. And then over here we have some of the most common circuits that are featured in that are used in products, and that can also be used in student prototypes. So the potentiometer, this is our knob that you twist. We've got some external push buttons to add on to the ones that are built into the microbit. We have some external lights of different colors. Well, we've got red, which matches what's on the microbit display. And then we've also got some greens and yellows and a multicolor. We have infrared detectors. We have transistors. We have infrared lights. And then all the resistors and wires that might be needed for a superset of projects to what we'll be discussing this week. So this week, with the exception of the speaker, that is now built into the microbit. This is an example of the first flurry of circuits that students will build up when they go through these lessons. So we've got our lights as analog outputs, or pardon me, digital outputs, binary outputs, push buttons as binary inputs. as an analog output, or analog input, we have the potentiometer down here, which you twist to get a number that corresponds with where you've twisted it to. And the servo would be an example of an analog output because it can rotate to and hold positions in a 180-degree range. And so we'll write programs, for example, to monitor the potentiometer. And as we twist that, the servo will mirror its action. And speaking of that, the Microbit also has, pardon me, a built-in accelerometer. And we're not going to be completely ignoring those built-in features. I'll stop the screen share for a second. Okay, can everybody see me okay?
Yes.
All right, good. Off screen, I am plugging in a battery pack to the setup. All right, just about ready. Okay, so here is a example that's using the Microbit's built-in accelerometer. And do you see how the servo continues to point upward? This little armature on the servo basically follows the direction of up. And then hopefully also there's some lights visible on the Microbit that are pointing up as well. So that's an example of something, like I said, that we don't ignore the things that are built into the Microbit. They also are tools that students can use to make even cooler and more interesting projects. Okay, do we have any questions so far before I continue? All right, well, feel free to chat them. Stephanie or Ari will bring those to my attention, and I will continue here. All right, so this kit is set up as a continuation after students have tried things like the very beginner tutorials for the Microbit that are featured on the BBC site. Incidentally, the BBC is the creator of the Microbit, and they gave them away to all of Great Britain's middle school students to get them started with and spark an interest in STEM. And what I'm going to do is start pasting links into the, where is chat? There it is. Okay, so let's see if this makes it through. Please tell me, folks, if you don't see that. I just chatted in the first link, and that is to the BBC Microbit. And actually, I should paste in a link to these slides as well. Copy link, slides, paste. Okay, so that's the slideshow. And so you can always come back to the slideshow if you wonder 6 months later, hey, there was a link to something that Andy showed me, and I wonder if I can find that. I don't see my notes from the workshop anymore. So this slideshow will be around, and so you can go ahead and find the link of interest in it, hopefully. So the first link is the BBC tutorials. And so there is a very step-by-step getting started in kind of a fun and interactive way with the Microbit. And these are just standalone activities. And they're recommended as a warm-up if the students have not already learned how to program in Python, because these are the very simplest of examples. And they're also examples that can cause some excitement too, like when we get to the radio, for example, they can send radio messages to each other. It's a lot of fun. Let's see, where is the compass? The compass is great too. So there's a compass example code right here that actually, after you wave the compass around for a while to calibrate it, it looks like there's 4, 5, 6 lines of code. And you can basically use that compass to figure out how to go in a particular heading after you've loaded this program. So these are the kind of things that we assume that the students will have gone through before starting here. Another example is from Make It Code It. And I'll paste that one in next. So the Make It Code It lessons are kind of a step-by-step thing. They've got all kinds of fun little activities to do with the microbit. And I recommend going through this, even though it is a slightly different flavor of Python from the one I just showed you. This is Make It Code It is Microsoft's version of Python. So you will see some differences. I think in a way that's good for students as well. Let's see. Okay, so this particular example that I selected only is available in the block coding version. So I think I'll back out of that. Let's try a different one. Here's our flashing sunbeam. Am I missing something? Do I need to? I wonder if I. Okay, first of all, I'll check the Python. See, I don't know if that's going to do it or not. Okay, so here is an example where, here we go. Okay, my mistake. So this one is the not the Microsoft version. This right here is the regular version, and to get to it, I had to click the Python tab. And so you can copy and paste this into your editor. And let's see, what is, yeah, and open in Python will actually take you straight to that editor. So pardon me, I misspoke about the Microsoft's version of Python for these. And so this again is another set of activities that students, or that you might want your students to go through before starting on some of the more in-depth material here in What's a Microcontroller. Now it does support 2 levels. We were talking about this just before the start of the workshop, because we had one teacher who was talking about middle school, incorporating this into middle schools. And so a lot of the earlier activities can be done in a connect it, follow the instructions, make it go kind of approach. And so a subset of the activities can be used if pre-engineering is not the goal, but you still have a list of curricular checkboxes that you want to get the students through with this kind of kit. If you go through it completely step by step from one web page to the next, then we are looking at a pre-engineering level of introduction. Most of the standards that apply are going to be on your CTE in the engineering, computer, and electrical pathways. We're approximating it at 40 class hours, and it can be used at the same time or in addition, or before or after the Cyberbot. Now, this is another device that can be connected to a microbit. Some of you might already be using it in your classroom. And as opposed to a more electronics and introduction to electricity type of approach, this has many similar lessons, but are being, as far as how electrical components are connected to an onboard computer, and you essentially get how they work inside a product, but from a kind of fun and exciting robotics approach instead. And so you can, for example, pull the microbit out of this kit that you have and connect it to your Cyberbot, and away you go there. All right, any more questions? Let me take a look at the chat and see It looks like Stephanie's just been quietly fielding the questions, so please do just jump in, because we've only got, let's see, we've got less than 35 attendees, so it's really not a problem if you want to just jump in and say, hey, Andy, I've got a question. Okay, so next up is getting started with your kit. So the starting point for all of our tutorials are learn.parallax.com. So I'm pasting in the main link right now, and then we'll go to that link. Pardon me. By the way, we are very close to the wildfires, so a little coughing is to be expected. It's not COVID. All right. So right up front, we can see that if you go by language and then down to Python, we have the Cyberbot, which I just showed you, and then the what's a microcontroller with Python and the Microbit. And that was actually the immediate next link on the slide. So I may have taken a slightly circuitous route to getting there. So these are the first activities we have the first chapters we have posted. These are prerequisite chapters that were already created for the Cyberbot, but work just fine as a precursor to these lessons. And so, for example, some of this may look familiar. See, so this is setting up the software, and then writing Microbit programs. I clicked the wrong one. Let me clean up my tabs here. All right, trying that again. Okay, so writing Microbit programs was part of the homework. And so if we're down here in make decisions, so here was an example we had you go through, and pop quiz for everybody. Is this indentation necessary, or is it optional? Thumbs
it's
up.
Necessary.
It is necessary. It is absolutely necessary. So if, for example, let's take a look at this program, and then my next address is going to be python.microbit.org. Okay, so if we take a look at this code here, I can say print. So we can do two things. So you probably just saw, hey, the display scrolled across that A was greater than B, but we can add in something like we can print to the terminal, A is greater than B. And now we're sending messages out to two different destinations. And in fact, I want to put this one before the display.scroll, because we'd have to wait for the display to scroll and finish its message before we got to the print. But my point in doing this is that if you have something and you want more than one Python statement to be executed as a result of that something, be it a repetitive loop, a for loop that counts a certain number of times, or an if statement like this, you have to have all of your statements that you want this condition to contain below and indented. And then once you want to, go on to something else, that's when you outdent back to the original level of indentation to continue. Does that make sense? I want to make sure everybody's really clear on that, because it's all right. I'm getting some thumbs up. Again, if you want to see other examples, or if a question comes up for you, please just jump in, unmute yourself and give me a shout out and we'll slow down. Incidentally, while we're here, I'll go ahead and plug in my Microbit, which might cause a slight glitch in my Zoom meeting display here. Okay, so the Microbit is now plugged in. So we can connect, choose our serial device. And then once we connect, like if you're disconnected, you can just download a copy of your program. When you connect, you can flash it right into the Microbit. So now we're loading the code. And that print statement I was talking about is something that you would see here. A is greater than B. And I hit this Control D to reset, to restart the program. And when I restart the program, you get this message and then the print result in this case. And at the same time, it is also displaying that display.scroll message. A couple of things about using this software. Closing serial to get back to the program. If I want to save this program while I'm connected, the way I do it is to, first of all, name it. So I'm going to take this simple underscore decision right here, that's the name of the program, and put that in the script name. Okay, now that I've named my script, to save it, just hit load save. And then this is important, download project hex. If you do that, what you have is this hex file. And a hex file is valid. So for example, if so here's my downloads. I'm gonna get the non-related one out of here for now. Okay, so here are my downloads. And here is accelerometer points up that I showed you earlier. And it's accelerometer points up. And then the second time I downloaded it, so it got appended with a 1.hex. And so I can drag that and drop it right into the editor if I have Windows actually. And then there we are with accelerometer points up. Then we can go back to the simple decisions that I saved. And there it is. And so if I want to change the name, like I could say simple decision take 2, load save, download. And then now simple decision take 2.hex is in my, let's zoom in on this a little bit. Simple decision 2.hex is now in my downloads. And you can move this to wherever you need to for storage sake. It just ends up in your downloads by default unless you've adjusted Chrome to put the file somewhere else. Another thing about load save is that it does allow you to add what are called modules to your project. And we'll take a look at that later, but I just want to mention that you can add a file and that file might do some special jobs for you where it substitutes 50 lines of code for 1 line of code that you have to type in your main file. And so sometimes we will add modules by clicking that button. And then sometimes you will want to download the Python version of the script, although that's usually in more advanced lessons. So for now, let's just focus on always downloading the project. Then if you want to open it and you have a Mac or I believe it's Mac that really mainly needs this. I don't know about Chromebook. If anybody wants to correct me here, just let me know. But basically, if I've got my file here, a file that I want to open, like for example, servo plot, I can drag that into that little gray box. So again, load save. Then you have a gray box. You can drag it in from your file browser, or another way is to just simply hit load save and then that or browse for file link. And then you can go through And there's simple decision take 2. And there it is in the editor now. So that's a quick little tour on the python.microbit.org editor and how to use it. It's not really your file select save from the file menu kind of user interface, but you can get everything done as far as opening, saving, and changing names of files. It's just that you're going to be setting the script name, and then you'll be using this load save menu. Okay, how are we doing, everybody?
Andy?
Yeah.
It looks like the thumbnails for the attendees are projecting over what you're displaying, so it's blocking part of your code.
Oh, for goodness sakes.
Surprise,
Okay.
Zoom, it always has something fun.
Yeah.
There, it seems better now. Thanks.
All right, thank you. Yes, I now have that on another screen and no longer intruding. Sorry about that. All right. So coming back here. All right, so let's now move on to setup and testing. That's a link you'll need.
Andy, one quick question before you
Sure.
get there. I actually name all my script names with the .py. So now I notice that my files are like .py.hex. That shouldn't be a problem, correct?
Correct. Yeah.
Okay.
It's only going to be the final the everything to the right of the last dot will be what's recognized as a file type. And if you find out otherwise, chances are low, but just let me know if you have any trouble opening any of your old files. And then we'll send out an all points bulletin about that if needed. Okay, thanks for that question. Are there any others before we move on? Okay, so did you all get that link? Breadboard setup and testing. This is the first activity that's part of the kit. And so almost every chapter or tutorial, we refer to the tutorial and chapter pretty much interchangeably, starts with a cover page, and that cover page will give you an overview. It'll also let you know what you need to be using. We've got some recommended previous activities or chapters that we want you to have tried before coming here. And then down here is essentially the table of contents. These are activities that you can do. And those activities are also along the left. And each activity is kind of a self-contained, okay, we're sticking to a fairly narrowly defined subject. And so connect the microbit to a breadboard is going to be our first thing that we do. And so here is a preview of how we want it to look when it's done. By the way, there's also page navigation down here. And so I just clicked the next page button to get here. And what this does is it first talks about some of the nomenclature that goes with a breadboard. And this breadboard is where students are going to be building their circuits, and to help just to help them get started with what is a breadboard about, we have this this animation. And I see that I did not get to my to-do item of adding the MP4 version of that animation. As teachers, you will often find that the MP4 version is really useful, because what it will allow you to do is talk about it at a rate that your students are ready to absorb, because of the fact that you have, unlike that animated GIF that's embedded in the web page, And almost all of the animated GIFs have a corresponding MP4 file that you can use, or that they can use if they want to hit play and stop to just follow along step by step. So for example, here's the entire breadboard. So that's the whole little tray that we're looking at. And then this area right here is called a terminal strip. And that's something that's a vocabulary item for the assessment materials. And then here's another terminal strip. And the terminal strip has letters for each column of sockets that you can plug wires into. And then they also have numbers for each row. And so for those of you who remember the 70s game Battleship, you can call out a row and a column, and then know that, hey, if it's on the right terminal strip and it's column G in row 16, we know that we want to put the wire into that socket. And there we are, socket G, comma 16. So that's our G is our X offset, and then 16 is our Y offset. There are also vertical bus strips on this one. And one of the things, I may be getting ahead of myself here, but so we have 3 bus strips. And for each bus strip, it has basically, it has a column on the left by the red stripe, and all of these little guys are interconnected. Then it has a column on the right by the blue stripe, and all of those little sockets are interconnected. So if you put a wire here, yeah, I am getting ahead of myself. Let's scratch that for now. So we stopped at, oh, my mistake. Okay, so here we have the plus column and the minus column. And as I mentioned, these guys are interconnected. Let's see what else we covered here. That was it. Okay. So moving on from there, now we know we have this breadboard, and there will be more about how the sockets are interconnected. So please hold your questions on that. So what we're going to do, first of all, though, is grab, or rather on behalf of your students or for yourself, either way, I'll get back to how to connect wires together. First, though, we are going to plug in the microbit to our breadboard and make it possible to connect things outside the microbit that are connected on this breadboard to these little pads here that are designed to be connected to the outside world via the microbit. So here is the next one where we've got the MP4, and I think I'm going to open this up and we'll just play it and pause it. Okay, so the first thing I want everybody to get out of their box is these 2 items, the microbit and the, pardon me, the edge adapter. And so I am currently diving into my parts. Now, the edge adapter will be in, I'm going to stop the share for just a sec. Stop share. Okay, the edge adapter will be, I'm sorry, the edge adapter is, yes, yeah, go ahead. The edge adapter is going to be in one of the gray plastic bags. And then the microbit will be in this little box right here. So, so go ahead and fish out the edge adapter from the gray bag and the microbit from this box. I'm going to do this with you so that hopefully I will go ahead and pull the microbit out of the foam that its pins there's some foam over some pins that are protruding from the bottom of the microbit. And then basically you'll fish get the green box open and get the microbit out of there. I believe it's also in a gray bag within the box. Man, that sticker really keeps the box closed. All right. So in the box, the microbit will be in a gray plastic bag. And this is going to be the point where I want to make sure that everybody knows to unmute themselves and say, hold on, I need another minute. And we'll go ahead and wait and make sure that everybody is with us. So once you've got the microbit and the edge adapter out of your box, you're going to plug the microbit into the edge adapter. Hopefully you can all see that on the screen. Stephanie, am I sharing the correct screen? Is that visible? Or Ari, either way, or anybody. Can you see the connecting the microbit to the edge adapter?
Yes.
Okay, very good, thank you. For some reason, the little green highlighter that tells me which screen I'm sharing just disappeared. Sorry about that. Okay, now the next thing that we're going to get out of the box is going to be that breadboard. I might be a little bit behind everybody. I need to get my microbit plugged in. Quick check on the microbit, although it actually, make sure that the buttons and the grid of 25 lights are pointing up or the same direction as the side of the adapter where you see some writing. The pins are pointing downward or away from us in this view. All right, so then everybody please watch this carefully. What we're going to do is basically put the pins that are sticking out of the microbit over the, so we're going to have this little P0 socket right here line up with the A30 socket on the breadboard, so that the pin labeled P0 that's sticking out of the bottom of the edge adapter will be kind of poking into the, we don't want to press it down yet, but it'll be poking into the A30 socket. And then some of the other pins in the microbit, these guys will be here and these two will be here. And by the time we get up to the 3 volt, well, let's move forward and see how that looks. Okay, so now the 3V pin will be in A11 and the P0 pin will be in A30. So just set it on there and make sure that those pins can start properly. And so now we're making the microbit kind of translucent in the animation so that you and the students can see where those pins should really be lining up. So everybody hopefully is watching the Zoom closely. And we also magnify so that they can just triple verify, hey, that edge adapter bottommost pin is in the A30 socket on that terminal strip. How do you guys like that? Do you think that's the kind of thing that can help your students follow these instructions and build circuits on breadboards and stuff like that? I'm hoping I can take silence as assent there. Or maybe you're all just so busy working that you can't unmute yourself.
No, the graphics are really nice because they allow you to check the alignment, so you're sure that you're not twisting sideways. So I really like the graphic and how you go in translucent to be able to show the position. Really
Okay, good. So this does look like something then that could work, not as in not become a classroom management hassle.
No, this is actually, this really helps. I used
Excellent.
it. Yeah, it really helps. It's pretty stiff to push the edge adapter onto the breadboard. It doesn't gliding like if it's an oily machine, you have to align it, but you have to push to get it in. It's stiff.
Yeah, I agree. And so what we did there, if you can see now, is we actually, once they've got it aligned, the animation shows, okay, those pins really need to go all the way in. Trying to back up and get it just right. There we go. So basically we show, hey, these pins sink all the way in until the little plastic headers that kind of hold the pins together are up against the breadboard. So make sure, everybody, to, once you've got your pins aligned and you press it in, to press it all the way down until the edge adapter meets the breadboard.
My only concern there is with students that we might get some pins bent with that because it's a little bit stiff. So it might take some practicing out, some teaching them to be very careful on their alignment before pushing. And we often tell them, if you put too much pressure, it's because you didn't do it properly, you didn't align it properly. Well, in that case, it's like you want to have a little bit of pressure, but not too much. So you want to be very careful. If you see your line, then push. But
that's a really good point. I'm taking that down in my notes so that we can have that ready for revisions. This is happening off screen. Thank you. Okay, so now that we've all got our
Andy,
yes.
I'm sorry, I was having connectivity issues, so I could see you but not do this. Could I quickly just put it together?
Yeah, let's go ahead and run through it again. Yeah, that is.
Yes,
that
thank
is
you. I'm sorry,
definitely
I could hear, but the video was stuck, like when the plug in the Microbit.
Yeah, not to worry. Let me get back to the MP4.
Thank you.
Oh, of course. All right. Okay, here we go. Okay, so so the first step is to find your Microbit and your edge adapter.
I did get through that.
Okay,
It was
good.
the breadboard.
Okay, so for the breadboard, I'll make it translucent so you can see and maybe zoom in. Okay, so what you want to have is on the bottom, you want to have the P0 pin, the pin with P0 and the label next to it in the A30 socket right here. And then everything else should follow. All the rest of these connections, just line it up first and make sure that you've got it nicely aligned so that these pins are resting in the plus and minus sockets there. And then there will also be some pins a little higher right here. So as long as your 3V connection is in A11, then you've got it all properly aligned. And then once you've got it properly aligned, what you want to do is sink those pins all the way into the breadboard until they meet the little plastic headers underneath. And it takes a pretty significant amount of pressure, as one of the other teachers pointed out.
Okay, I think I almost got it. I'm
Okay.
having my son help me with that.
Ah, excellent.
Okay.
You brought a test subject with you.
Yeah. Oh, I got it. Okay, thank you so much.
Okay, and thank him for his
Okay.
help.
Yeah. This is
All
fun
right.
for him.
Well, yeah, at Parallax, we kind of enjoy it maybe a little bit too much as well. Okay, and yeah, we also use that as kind of a barometer for what's going to be fun for the students. Okay, so now that we've got the, oh, incidentally, going back to the previous page, in addition to the animation, we have it in writing in a step-by-step fashion. So it kind of, so they can use this to verify that they did it correctly before moving on. All right, so the next thing that we're going to do is, remember I was talking about measuring continuity. And so let's ignore the beeping noise for now, because I think I have that feature disabled, but hopefully it's visible in this animation that when you have two wires in different rows, they're not connected, and you get the little not symbol. And then if you plug wires into the same row, you get a little check mark indicating that they are connected. And that's on the display of the Microbit. And then you can see here, what the result should be for when they're on the same row or a different row. And so that's a first step into electrically connecting two wires together. And so okay, terminal strips for electrical connections. Okay, so we're going to talk about this again in a slightly more gradual approach. For some of you are familiar with this already, but for those of you who are not, we have, as I mentioned earlier, two terminal strips. And in each of the terminal strips, every row of 5 sockets is a row that you could plug anywhere between 2 and 5 wires into to electrically connect them, so that current could go in one wire and come out another, for example. So all of these are connection options. So if you have 2 wires and you want to connect them together, you could, for example, connect it into G and H1, and they'd be connected. Or you could connect them into G and J1. Or you could move down here instead and connect them into F and J7. As long as it's in the same row of 5, it's a connected pair of wires or part leads. And so that's what we're showing here. And then what the steps in the activity are going to have the student do is, so pick a row of wires, and you can plug in 2 wires, and they're going to actually examine this step by step and try to predict, okay, do these 2 wires follow that row of 5 rule? Great, they're connected. Now let's plug in a 3rd wire. So after that, because these 2 wires right here and here are not on the same row of 5, they're on separate rows of 5, it means they're not electrically connected. Now, with a 4th wire, we've got several different things happening. The first is these are in the same row of 5, so they're connected. These 2 are not in the same row of 5, they're in separate rows, so they're not connected. Likewise with these 2. And then up top, these are in a different row of 5, so these 2 are connected to each other. Now you can also go to another row of 5. It's the same row, but it's a different row of 5. And so an important distinction here is that, yeah, these two are connected to each other. And so are these two connected to each other. But those two are not connected, nor are those other two. And one last example. These are on the same row, but different rows of 5, so they're not connected. But you can take a jumper wire and put it from one row to the next, and that adds the conductive metal you need, so that now those two wires, which were not connected before, are now electrically connected. Okay, how's that? Are there any questions about that example? Okay. So that's an intro, and see, we talk a little bit more about, let's see here. Yes. So there's also bus strips, and they are in columns. So the column to the left of the red stripe is a way to connect a pair of wires, and the column to the right of the red stripe, pardon me, and the column to the left of the blue stripe is another place where you can connect two wires. And in this example here, we have a wire that's connected. Let's see here. Okay, so for the bus strips, the rule is that it's a vertical connection. And bus strips, by the way, are what are typically used to supply power to other circuits. And by making this vertical, what it makes possible is that you can connect power to any row. So you might have a little circuit up here on these rows. Well, you've got power on the left and right. You might have another circuit down here, and you still have power on the left and right. And so these are usually for your supply voltages, which in our case is going to be 3.3 volts in ground. So these two guys along the left here are connected because they're in the same column. And then we add this third wire. And because of the fact that continuity goes along the column, this red and this black wire are not connected, even though these two reds are. And now we're in a different column. So one of the things that I've seen students get confused about is, well, gee, I connected it by the blue stripe, so aren't they connected? And the answer is no, they're not connected because they're not in the same column, just like they wouldn't be connected on a terminal strip if they weren't in the same row. But you can also still do that trick of using a jumper wire to connect two bus strip columns together. And then, yes, your wires will indeed be connected to each other. All right, so with that out of the way, let's move on to testing that all out. So the next thing I'd like you all to grab from your parts box are two of these 3-pin headers. The red alligator clip, the black alligator clip, one red jumper wire, two black jumper wires, and an extra either blue or yellow jumper wire. Might as well make it blue just to exactly follow the instructions. Some students ask, does the color of the wire matter? Yes, for the sake of describing the connection at a glance. So for example, we use black to connect to the negative battery terminals. We use red to connect to the positive. We also use red and black probes. And then for just a plain old wire that might be connecting something inside a circuit, we use either the yellow or the blue. So anyway, grab these parts. And I'm going to grab them out of my kit to try to get a feel for how long I should wait. And if I still went too fast, let me know and we'll give you some time. The 3-pin headers are going to be in a bag of loose parts. One thing you can do is if you have a bowl or plate handy, you can upend that bag of loose parts. The other thing you can do is pull everything out of your little Microbit box, the box where your Microbit came, and just upend the bag into there. And that'll make it easier to fish parts out of it. Okay, does anybody need more time? Give me a shout out if you do. Okay.
I see some heads shaking no, but I see a lot of heads concentrating on what they're wiring.
Thank you for the heads up. Although
Maybe,
they're still fishing for parts.
okay, I do see one thumbs up. I see some bags opening.
Okay, thank
Another
you.
thumbs up.
So Andy,
Yeah.
just Diane, I have a question. Like, how would you manage this with the students? Do you look at the lab that you want them to do and only give them the parts that they need? Or would you give them the whole kit? Because I could see me having like little resistors and stuff all over my classroom.
Yeah. One of the things that is helpful is there's a number of different kinds of plastic Tupperware containers that can be purchased at, say, Walmart or the dollar store. And those are good for keeping all your parts together so that they don't necessarily spread far and wide. Yes, another thing as far as class management goes is I need to find the master parts list for this. I believe it's on the product page. I'll have to check that. Is to give the students the Tupperware container, the kit, and the master parts list and make them responsible for returning all the parts at the end. Another thing in terms of classroom management is that typically we recommend getting a couple of extra small parts kits, which Stephanie, can you help me with the link to that by pasting that into the chat? That there is basically a replenishment bag of small electrical parts that can be purchased. And then if you have several of those on hand, when students have ended up losing a resistor or a 3-pin header or something like that, there will be an extra part that you can give them to replenish their kit along with whatever penalty you deem appropriate.
Okay, thank you.
Certainly. And how are we doing now for having fished out all the parts? I think we're probably ready to move on. Just stop me if not. Okay, so here is another important. All right. So we're going to start with these parts. Oh boy, that's hard to see because of the scroll control. Okay, pause right there. Okay, that's inconvenient. Basically, the 3-pin headers should be plugged into the breadboard over in the same row as the P2 and the P0 labels. Let's see if we can get that to be more clear. Okay, I might just download this. And then open it. Okay, let's try this. Okay, it's a little bit more clear. Can you see down here where we put the okay, so now hopefully you can see the location of the 3-pin headers next to P2 row 28 and row 30, columns C, D, and E on the left terminal strip. There. Okay, so make sure to get those going. And then after you've got those plugged in, we're going to have you grab the end of a red jumper wire with the end of an alligator clip and the end of a black jumper wire with the end of another alligator clip. And then the other end of the black alligator clip goes to the 3-pin. It should grab onto the 3-pin header that's in on row 28. I'm going to move forward here a little bit. Nope. Okay. So, so the red alligator clip should grab the 3-pin header that's sticking out of the row that's at the same level as P2 of the adapter. Black alligator clip, we want to grab onto the 3-pin header that's next to P0. Again, these 3-pin headers need to be going all the way into those sockets. And then on the other end, we're going to start just like the animation did with 2 wires in different rows so that they're not connected. There's a close-up. So that's rows 16 and 17.
Andy,
Yes.
will I electrify myself if I leave those? I have the batteries on my Microbit. Is that okay, or should I take them out?
Well, best practice wise, it's best to remove the batteries from your Microbit. Yes. As far as electrocuting yourself, don't worry about it. You won't be able to hurt yourself. And the Microbit overall is pretty robust and difficult to damage, but you know, the main thing most electronics teachers harp on their students about is disconnecting the power before they make any changes to a circuit. So we always want to have the power disconnected before we start plugging and unplugging jumper wires. Now there's going to be an exception to that since we're using these alligator clip probes as a measurement device. So we are going to leave the power connected while we're using these.
Andy.
Yes.
The alligator clip, is it on the 3 pins on the 3-pin head, or does it just need to be connected to one of them?
That's a good question. Get as much electrical connection as you can out of that. So if you can grab all three, that's going to be the best. And a nice, that'll give you a good, strong electrical connection that won't accidentally open up as you're moving around the clips, or as you're moving around the other ends of the clips to take measurements.
Is there I always have a hard time like unplugging the battery from the Microbit. Is there like, you know how sometimes you press it the side or something, an easy way, or just like yank it really hard?
Yeah, avoid the yanking it really hard. If you can lift up the, let's see, do you have it plugged into the Microbit itself or into the adapter?
I have it plugged in the Microbit itself.
Okay, let
It's
me try that
needed
out.
3 AA batteries.
Yeah, so normally the plug has some little lumps on it that get stuck that it's trying to prevent from.
Did you say 3 AA batteries? Or do you mean 2 AAA batteries? Is it the one that
Yes,
came
I'm
with the
sorry.
Microbit?
Yeah,
Okay, good.
exactly. Yeah, 2 AAA.
Okay, I was just concerned about your voltage level there for a moment.
Okay, thank you. Sorry.
It's okay. Incidentally, we do sell just replacement battery packs that have a power switch on them, so that you can turn it on off without having to remove the batteries or disconnect that.
That's a great idea.
I'm hoping that they become more standard in the future in various kits, because that
Okay,
is
so
convenient.
sorry about that, Stephanie. So for now, yeah, go ahead and you can either try to grab the little wings that are sticking out from the side of the plug and jiggle it back and forth a little bit as you're pulling. And if that doesn't seem to work, then yeah, go ahead and just give it a firm pull, just holding onto the wires. Not normally recommended, but that will get the job done. Okay, so are y'all ready? Let us continue then to the script. So after, and this is a typical pattern. So after you do the circuit, the next thing to do is the script. And I'm actually going to, so heads up, basically we have here continuity tester.hex. And if you're on this page, what you want to do is right click and select Save Link As. And then it'll allow you to download it. And I'm waiting for my screen to come back. There it is, saved. So I'm gonna copy this page link, and we're gonna have you all right click and download. Where is the chat? Okay, to everyone. Paste. Okay, there we go. Okay, so go to the page that I just pasted into the chat and right click and download continuity tester.hex. And then we're going to open that with the Microbit, the python.microbit.org editor. So there's also a link to the python.microbit.org editor right below the continuity tester download. So after you've downloaded continuity tester, right click python.microbit.org and open it in a new tab. And if you've got Windows, you'll see continuity tester.hex in your recent downloads for Chrome. And you can literally just drag it and drop it onto the editor pane. I think that works for Chrome too. If you have a Mac, you need to hit load save and then drag and drop continuity tester into the gray box here. And give me a shout if you're stuck at all on this. I'm just gonna show what I want the end result to be here in the window.
Hey, Andy,
Yes.
I'm using a Mac and I was able to just drag and drop it, but I have an updated Mac. My Mac's updated to the Big Sur.
Well, long live Big Sur. I'm so glad to hear that.
Yeah, drag and drop does work.
Oh, thanks for the update. That's great. Yeah, on earlier versions of Mac, you would actually just see a bunch of numbers. It was very confusing. Now, when you, the next step for those of you who are ready for it is to find the long USB cable and plug it into your computer and into your Microbit. And your new Microbit, I don't know, you've probably heard mine making a racket because it had that default program that the Microbit comes preloaded with.
Andy, did I miss something? But I haven't used like this blue little cable.
You have not used which cable?
This little blue.
Yes, the blue is coming later.
Okay, okay, thank you.
Oh, certainly. Okay, so I'm going to load this into my Microbit, partially to make it shut up. Flash. And when you get a new Microbit, it takes a pretty long time to flash because it loads a new runtime into, wow, that was actually super fast. Normally, it seems to take a long time to load code because it's updating the runtime in the Microbit. But it looks like this one's oh, that's interesting. So my Microbit, did anybody have trouble like loading a program into your new Microbit?
I had some problem and I had to change of USB plug on the laptop.
Uh-huh.
And sometimes I had to plug and plug a few times before being able to do it. That it worked.
Okay. Yeah, that seems to be happening for me right now. Actually, since
Yeah,
I'm
I
stuck
had a
presenting,
trouble
I'm
too.
gonna grab the other Microbit for the servo demo and set that other one aside for now. Connect. Okay, so for the sake of anybody watching the video later, what I did to load this script into the Microbit was I hit the connect button, then I hit flash. And I believe the instructions say next to hit the open serial button. No, it doesn't matter. It's displaying on the Microbit, so the open serial button doesn't come till later. All right, so once you've got this script running in your Microbit, the next thing to do is to, and this is important for the sake of really gaining, for the students really gaining an organic understanding of how continuity works and when it happens and when it doesn't. This is the kind of thing that in previous books, all of the books that I've written, it's been like a page or two where we've shown a picture and talked about it. And what I want the students to do here is to really get into their hearts, how does continuity work? When are two wires connected to each other? And so the idea is, after loading the script, you should be able to see a check mark when the two wires are in the same row, or a not connected circle with a line through it when they're in a different row. And so let's all try that, make sure it works.
Andy, I have like a little 0 on it.
Yeah, so the 0, it's actually my best approximation at a circle with a slash through it.
Exactly.
And so that's the not, as in no crossing type of not. So it's saying not connected. And so when they're in 16 and 17, you should see that not. If you unplug the wire from row 17 and plug it into row 16, then you should get a check mark.
Okay, unplug the 16 and put it in 17. Okay, got it.
Yeah,
Let's see.
actually, I got a little bit dyslexic on you. I meant to go the other direction, but
Well, I'm
but-
dyslexic, so all this and right.
Yeah, and it was vertically dyslexic even. But yeah, as long as you can enforce the rule that you get the check mark when you're in the same, when both wires are in the same row of 5 sockets, and then the not connected when any other situation, be it the wires are sitting on the table or connected into different rows of 5, any of those should give you the not connected. Something that I don't know that we have documented, but you can actually just press the 2 metal parts of these wires together, or even the 2 clips, and it'll show you the connected symbol as well.
Okay.
So in the few minutes that we have left, I'll just go ahead and show you and leave it to you to try out. But an earlier animation, I lectured about how continuity works. Well, this animation and the step-by-step instructions are having you go through all those connection options. And the blue wire, incidentally, comes into play when you want to connect these 2 rows together to see that you are connected. And we also do the column tests. And that's where the second black wire comes in, because the second black wire is going to jump 1 negative column, 1 blue line negative column to the other right there to verify that it's connected.
Even when I put them in the same row of 5, like 17, I still have the 0.
Oh, okay.
Why
So
can't-
when you so the best thing to do then is to check the connections, like your 3-pin headers. You want to make sure that 1 3-pin header is fully plugged into the row right by P0, that same row of 5 sockets. And then likewise with the red alligator clip, we want to see that in the row by P2. So it's rows 28 and 30, columns C, D, and E for both of those 3-pin headers. Then make sure that wiggle each alligator clip a little bit to make sure that it's nice and scraped up against the 3-pin headers, has a good grip on it. And then likewise, check the alligator clip's grip on each wire.
One problem I had is with the alligator was touching the plastic sheath. And so that was not making contact directly with the metal. So I had to adjust the alligator on the red and black wires to make sure it was attaching properly to the metal. It's pretty obvious, but that was, you know, when you go fast, you might not notice.
Actually, we're going to add that to the text. Thank you so much for pointing that out, because students will do that too.
Thank
We want to
you.
add a little exclamation box that says, hey,
Yep.
make sure to grab the exposed wire, not the plastic.
I did, and I already added Nicholas's suggestion to keep the alligators apart, adjust the plastic covers so the probes themselves aren't touching over by the 3-pin headers. So thank you, both
Perfect.
of you. I'm editing those this moment.
So folks, have we all been able to now measure continuity? Thumbs up, thank you.
I
Thumbs up,
still have a
beautiful.
problem. And
Okay.
I don't know what's, I
Well-
checked and those 3 needles are.
So what we
inverted.
can do is we can screen share after the session.
Oh, okay.
And let's get you unstuck. And then anybody who wants to stay and is stuck on anything, you are more than welcome to stay. But what I want to do is quickly talk about what we'll have you do for next time. And so I have to bring up my email here, drafts. Okay. All right. So here is an email that is going to appear in your inbox very soon. Okay. And okay. And what we're going to do, I'm really not sure why I'm asking you to go to make sure that you've got a battery holder and AA batteries, but it's not going to hurt. So you'll need the AA battery holder for Friday, for your homework between Monday and Friday. But we do want to make sure ahead of time that you have your AA or your AAA battery holder, your AAA battery holder that holds 2 AAA batteries. We want to make sure you've got that, and a pair of new alkaline AAA batteries. Okay, then this is the circuit that we're going to have you build. And what we're going to have you do is you'll be able to, I list the activities further down, but this is basically the master circuit that we'll be using for Wednesday. So I just want you to make sure to disconnect power before you do this, and very, very carefully follow the instructions on all of these connections visible in this picture. This is the schematic for it. We'll talk more about that later. These are push buttons right here. And the way you insert the push button into the breadboard is going to be very important. We want the little legs that stick out of the push button to be sticking out of the sides as they go into these sockets. So the tutorials that are going to walk you through this are connect and blink a light, which looks like this. So this will be your first circuit, and then there'll be a script to test it out, and you'll want to make sure to go through, and when you load that script, you'll want to verify that the light goes on and off. Then we're going to measure that light with a voltmeter. We'll have you try out that activity and do its script and tests. And then we'll have you measure the light with the Cyberscope's oscilloscope. So basically build all this up, and then you'll be measuring pretty much the yellow light. It'll say the green light, but if you've got this built up first, there's a step where the green light gets moved down to the P13 socket. So it's okay that you're doing your tests on that yellow light that's connected to P14 right here. And well, just know that you can build this whole thing up and that you won't have to take anything apart. It will show you where to connect the probes to measure voltages, and that'll be fine. And you'll be able to measure those. I will show a little bit more about some of the basic measurements before we get to this. This is skipping a few steps. So I'll show you a little bit about some of the steps that we skipped, and then we'll go through and start running scripts to make these lights go, to monitor these push buttons, and take the result and make the lights do things. And so, so do your best to get these all built exactly as shown, and then follow these links because they're going to have instructions on putting everything together. So you'll start at connect and blink the light, and then you'll also run the script and tests for blinking the light. And then likewise with the measurements with the voltmeter and with the oscilloscope. And each one of those is going to take you to a step-by-step, okay, you're going to put your black probe here, you're going to put your red probe here, and then it's going to do the, and then moving on to the script and tests, you'll be able to download the script, open it, load it with the Microbit, the python.microbit.org editor as we just did, and then it'll tell you to go over to the Cyberscope application, which is at cyberscope.parallax.com. You can just follow the link. And when you hit connect, it says disconnect because it's currently connected, you'll actually see the on-off pattern plotted graphically. If you have any questions whatsoever along the way, please email me. I want to help you get past any hurdles before the next class starts. And ideally, if you can try to reach me, say, try it out tonight, try to reach me tomorrow as opposed to the morning of the next class, because I'm not always super available. It's kind of tough to catch me on the morning of a given workshop. So do your best to get those done as quickly as possible. Make sure to contact me if you get stuck on anything. I will go ahead and send this email now just to make sure you've got it in your inbox. Okay, there we go. Okay, and then we will keep going. That concludes today's workshop. We'll reconvene at 1 p.m. Pacific on Wednesday, the 15th. And what we can do is keep going for a while with some informal questions and answers, but I also want to give top priority to anybody who is stuck. So for example, if you're stuck on the continuity measurements, let's make sure to get anyone who the continuity measurements aren't working for unstuck first, and then we can take some general questions and answers. Sound good? Okay. Oh, yeah. So I have a question from Norman about the long legs on the LEDs. So when building the circuit, now I got to get that email back up. And this is discussed in the step-by-step instructions. But yeah, let's just make sure that we talk about that here. Just about got the email reopened. Okay, here we go. All right, so what Norman pointed out is that these lights are like little one-way valves, these LED lights, the red, green, and blue LED lights right here. And these little, the lights have two different lengths of pins. And so we want the longer pin to plug into the left side of the right terminal strip. So where you see these pluses next to each of the LED light pins, that's where the longer pin goes. And then the shorter of the two pins is going to go along the right there. All right. Let's see here. Next question. Will we have access to a recording of this session? Yes, I started recording. I have not yet stopped. And I believe Ari may also have a local recording. So anyway, as soon as possible, we are going to get the recording up to YouTube, and then I'll go ahead and send out a link so you can refer back to parts of this, of today's workshop as needed. All righty. Let's see.
Andy, I still have the 0. I really don't know what.
Okay, so let's, is it possible for you to, unmute your video and hold up your setup in front of it?
Yes.
Okay.
Do you see it here?
Yeah, your virtual background is making it,
Oh,
okay. Oh, no, it's better there. When you're holding it in front of your sweater,
Yes.
it's visible, but when you hold it anywhere
see.
around you, then it's not so visible. So just hold it like at shoulder level here. Okay, I can see it. Okay, now, and then are you in the same row of 5 right now?
Yes, it's 17.
Okay, so they're both in 17. Yeah. I'll be darned. Okay. Try just pushing the two alligator clips where the wires are connected. Try pressing the middle of the alligator clips against each other. Does that give you anything? Or yeah, go ahead and connect the two alligator clips to each other.
Oh, to each other.
Yeah, have them basically bite each other.
Okay.
Bite each other's
So out of the
jaws.
cable and bite each other
Yeah.
like this.
Yes. All right. So now on the other end, we still want to be connected to the 3-pin headers.
Yes, they're there.
All right. So now what do you see?
Still the 0.
Okay. So now let's go ahead and disconnect the alligator clips from the 3-pin headers and just verify that that you can see P0 is on the same row 30 with the lower 3-pin headers.
Yes.
Okay, here I'll go ahead and
line up with P0. Do you see it?
yeah, it's hard to see. Can you see it in mine? I'm trying to get focus here.
Yes, I see it. I have it in the same spots. There is only like one tiny row in between of them, right?
Yeah, so there's one socket in between P0 and your 3-pin headers. And then there should be one socket in between P2 and your 3-pin headers. Is that right?
So there is one row and one, okay.
Oh, I see. Yeah, there is also an empty row 29.
Yeah, row 29, right?
Okay, perfect. Now
hold
the
on,
next thing, here's the next thing to try. Pull the microbit out of the edge adapter socket and then press it back in and make sure to press it in firmly.
Out of the sockets,
Yeah.
press it firmly. Inside, right?
Yeah, so the microbit, we want to pull it out of the edge adapter socket. Can you see me?
Okay, yes.
Okay, so we're going to pull it out of the socket
Okay, I
and then
did.
press it back in.
Yes. So see, I pull it out and it still shows the 0.
Uh-huh, yeah, and
It should-
that's okay.
That's okay. Okay,
the
so now I
main
put it
thing-
back in.
Well, actually, tell you what, let's really make sure that your microbit isn't possibly, let's make sure nothing is defective. Okay, what
Okay.
I just did
Mhm.
was I pulled out the 3-pin
Yes.
headers.
Yes,
I'm back to an empty board.
yes,
Now, what I'm going to do is I'm going to take a wire
yes.
and I'm going to connect row 28 to row 30
Mhm.
in that same row of 5 with P0
Okay,
and P2.
okay.
And by George, we had better have, I don't know if I have, yeah. Oh, wow, I have it not connected. Okay, it's because I didn't plug it into the right row.
So I take the little needles.
Yeah, you
out.
were between 1 and 2.
Yeah.
So I put it between 28
And 30.
and 30. Okay. Hold on, let me make sure. 28 and 30. Okay. I have that now.
All right, now do you still have the not connected circle or do you have a check
Okay.
mark finally?
Let's see. I'm coming. Now I have a check mark. Yeah.
Okay, good. So we know that something outside of your main system is responsible. It might, like, I'm imagining possibly
Mhm.
a bad solder job or connection inside one of the alligator clips. So let's try this game with just different colored alligator clips. now.
Okay.
Let's go ahead and
Yeah. I'll use the green and the yellow. We have lots of these at home, so.
Okay,
my son
good,
can
good.
get-
Now, one thing I'm noticing is that these 3-pin headers, actually, I just pushed some of the 3-pin headers out of the little plastic.
Uh-huh.
So you see the
Yeah.
little black plastic
Yes.
holder for the
Yes.
pins?
Uh-huh.
When I press down, the pins just pressed upward. So we want to make sure that the pins sync well
Yes.
into each.
On either side I put inside, it's the same, right?
Yeah, yes, it is. You can,
Okay, so I put.
there
it
is
on
no right
30,
side up or upside down on those
Okay.
3-pin headers.
And I put at 29, correct?
28 and 30.
28, sorry, yeah, 28, yeah.
Yeah, I
And
put
then-
mine in 29.
So I put it there, and there is 29 in between, right?
Yes,
So
exactly.
now I take the new alligator clips, right? And I'm
Yeah.
gonna do white where black was.
Good idea.
Okay, just a second. And I do the 3 pins, right? And now I do the other one. And then I will do yellow or red.
And then once they're connected, once the yellow is connected,
Mhm.
now you have yellow connected to what, P2?
Yes, that's right.
Okay,
So
and then,
yellow instead of red.
all right, so now.
Oh,
let's-
now I have a check mark. Yep, I have it.
Okay, now do you have the yellow connected to the Okay, let's see. here.
Yellow is where red used to be. So
Yeah.
it's in P2 and it's in my red.
Oh, and you've already got the wires testing. Now, are those wires in the same row of 5 currently?
Yes, they are.
Okay, so now let's try,
So I got my check mark.
okay, now try unplugging one of them and let's see if we go back to the not connected.
Oh, okay. Yes.
So
we should
unplug
do-
one of the wires from
Yeah.
row 17.
Oh, from row 17.
Yeah.
Yeah, I unplugged one of them.
Okay, now what do you see on the microbit?
It's 0.
Perfect.
Yeah, so it's working. So now maybe I just test which one of the alligator clips was defective, right?
Yeah, that's excellent. Yes.
Right. Okay. This will do. So I'll start with black first. See if black will work nicely. And then we can, okay. So I'll put it. Oh, that's such a relief. At least it's just the alligator clips, right?
Yeah.
Yeah, that
that's-
works. So black works fine. I think it's maybe the red. Let me double
Okay.
check now.
Another thing that can end up happening is through handling the clips, you might have ended up reestablishing a weak connection. So I would say let's stick with the yellow and green. Continuing on.
It's the red. The minute I put the red, it just
Okay.
goes to 0.
Okay. All right then.
Thank you so much.
Oh yeah, I'm glad I could help out. And
Thank you.
I'm glad it turned out to be a probe and not the board, because we do a lot of testing.
Yes, I appreciate it. Thank you so much.
Oh, you're very welcome. Yeah, we do a lot of testing on our edge adapter. And so I was, internally going, oh, I hope it's not the edge adapter. I hope there's not something faulty about our
Me
test.
too. I was hoping of something that I can continue. This is fun training. I don't want to miss out on anything.
Okay, excellent.
Thank you so much. This is fun. I had so much fun with the exercises.
Oh, that is fantastic.
Yeah, I can't wait to help my students getting their hands on this. It's kind of fun.
All right. Well, and so I
have a
emailed out the
question,
homework.
Andy.
Yes.
Hi,
is this
Andy. I have a
Anna?
question. This is Anna. Yes. So I'm getting an error when I do the USB connection. It says, please reconnect your microbit and try again. No device selected. When I do the from the Python microbit editor.
Okay. Let's see. Do you have a share screen option on your Zoom?
Yes, I have a screen. Yeah, let me share my screen.
Okay.
Yeah, so this is what I'm saying.
Okay, so go ahead and hit close.
Close.
All right, so let's try from the beginning.
Okay.
Go ahead and click connect.
Connect.
And then, okay, yeah, that doesn't look right, but let's try it. Go
Yeah.
ahead and click the BBC Microbit CMIS DAP. So click, see where it says BBC Microbit CMIS. Yeah, okay, then click connect.
Oh,
Okay.
oh God, I see it worked. I think this is where I was stuck. So I had
Oh,
to
and look
click
at
on
that. So there's that
line.
initial, yeah.
Yeah, this is the first time this portion worked. So I think in the instruction, it didn't say that you have to click on that line. So maybe that.
Okay, Stephanie,
was
did you
the-
catch that?
If you could repeat it, I'll get to at which page I need to be on. I can fix it
Okay.
now.
So when you do
Yeah.
the connect, when you do the connect, the screen opens up, and the instruction didn't say click on that line.
Actually, we'll have to reconvene on that one internally
Okay.
because
Yeah.
basically that is an earlier. I think that the problem is that we're taking you on too much of a whirlwind tour, because that is an earlier step.
Oh, I see.
And so by the time that we've gotten to here, it is intentionally not included.
I see.
The idea is that we did it earlier on. I'm trying to figure out how to help with that. I'm probably going to have
Maybe
to.
a remember you need to do this kind of thing.
Yeah, we might need to add those here and there.
Yeah.
It's just, yeah, thank you very much. I think it's now working.
Okay, thank you. And then you can go ahead and unshare your screen.
Okay.
Yeah, and I confirm it is in the, I'm seeing the documentation in the actual testing the Microbit for the first time. It says click connect button and it says to connect and it shows in detail. But
Okay, okay, thank you.
Okay, and then I'm going to go back to the chats. See if anybody else.
The graphics and the instruction, like with the animated GIF, really help on the website. Really like these.
Oh, good. Thank you. Is that Sylvie who's speaking?
Yeah, this is Sylvie. Yeah.
Okay.
It really helps because it really shows the step by step, and you're able to go back to it, and it's going to be very helpful with the students. In one of my things, I'm working on the homework. Sorry.
Oh, no. By all means, ask away.
I see, there's the resistor that you're connecting from A9 to E15. It's a long distance, and the length of the resistors is pretty short. So that's a little bit tight. So I bend the edges and it goes in somewhat, but I can't push it all the way in, but it's making contact with the metal. So I should have contact, but that's something that students will struggle with because of the distance. If they push all the way in, then they will be struggling about the length of the leg on the other side to be able to push it all the way in. They're gonna have to manage and share the legs instead of having some extra room, and it's
Yeah, I'm hoping that my camera will be able to show you this, because this is a thing that I'm stumbling across the hard way. This is part of the supply chain issues that we have run into. And I'm going to have to speak with our supplier about this because I am seeing, can you see the two wires that I'm holding?
Yeah.
Do you see how one is shorter than the other?
Yeah.
So this one with the longer wires is from an earlier vintage of the kit.
That's why. Yeah, because even in the kit that I receive in all the resistors, all of them are short, but two have long legs. But they're the wrong color, so they're the wrong resistance. So it looks like there's a mixture of short leg and long leg. So that's something to have an alternative option, or maybe an alternative schematics when we're working with short leg.
Yes, we'll need to add something in there about bending the ends of the legs. So for example, if this is 100 ohm resistor, so it's not the right value, but essentially, if we can bend each end down, that hopefully will bridge the gap.
Yeah, and actually, I can show you. I can activate the camera.
Okay. Yes.
So just ignore the mess. So I don't know if you can see. This is the banding. So I have it's less than a 1/4 inch. It's probably, I don't know, it's more than an 1/8 of an inch, but less than a 1/4 inch.
Okay.
Band on either side. And when I do it this way, the resistor is flat on the breadboard.
Okay.
But I'm able to have contacts on either side. So you can see it's really tiny.
Yeah, I'm glad. Thank you so much for bringing this up, because I'll want to send an all points bulletin to the attendees so that they're aware of that.
Yeah. because that's something is that if we ask the student, or for me, the cadets, to be pre-bending, then they won't be as disturbed by that. But if they start with the resistor when the legs are still straight, the typical habit is going to be, oh, I push this one in, then I bend it, then I put, oh man, it's too short.
Yeah.
Well, if it's pre-bent, it will be less of a struggle. They still have to play with it because it's a short distance, but that will, they might be less struggling with it.
Yes. I can make a drawing quickly of the shorter one with the ends bent down. We'll go ahead and get that out to everybody.
Well, and
And
that we're doing that ahead of time. That's one of the big thing I always tell the educators I work with: test everything before you do it with the students, so that you figure out some tips and tricks that you can give to your students or cadets prior to the class. You don't get stuck in the middle and
Yes.
like, oh, well, what do I do now?
yeah. Yeah, well, and I think that a number of workshop attendees are also going to run into this. So I'll try to get an all points bulletin out to everybody as soon as possible.
Yeah, no rush. I just thought, I'm kind of keeping track of all that, so that, because my cadets are between 12 to 20 years old. Some have done a little bit of electricity and circuitry, and some have done none. So it'll be interesting.
Yes, I agree.
So, Sylvie, quick question. Are you in Washington State?
Yes, I am, sir.
I just
Where are
came. I just arrived. I came a little late because I was flying from Spokane.
Oh, yeah.
So,
Well, yeah. Yeah, I'm in the Seattle area.
yeah,
And,
West Side.
I'm kind of like a multifaceted educator, because I work in elementary and secondary Montessori school, where I do STEM classes. So I will do electricity with them and electronics and programming, but also work with the Civil Air Patrol. And I do, I'm an aerospace STEM and cyber education officer. And so we do this thing, transitioning from electricity to electronics and robotics, including programming. Then we go into cybersecurity. And
Nice.
so, and I met Parallax through NYSERC, that is now cyber.org. And I'm so glad that we found you, and I've been to some of your presentation, and I've learned a lot. I really like how it's done. It's very pedagogic, and the schematics are clear. The videos do help a lot, and it's been good. So now we're looking for funds to make some big orders and have some electronics and programming workshops and robotics camps next summer. So
Nice.
Yeah, that's excellent. One nice thing about this kit is that it's for quantity one, I believe it's $89. So it's not as much as, say, a $200 or $300 robot. So it's easier to get it into the hands of students. We put in quite a bit of effort to try to make sure that the cost of the parts didn't drive the kit up into the hundreds of dollars.
no, and also parts of the electronics, like we have lots of breadboards, we already have some resistors and all that, and the fact that we can purchase the edge adapter and the microbit separately also help. But the kit in itself now is a decent price, and I know for what we're doing electronics and programming, it's better to have a larger quantity of these for them to study that part than have a smaller quantity of robots, because for the robots they can work in group. Well, for the electronics, you want smaller group or individual work, and having access to these kits really make it more approachable for nonprofit organization or small groups. So no.
And one thing that's really cool about it, although we're kind of getting ahead of it by talking about it now, is just that you get a multimeter and an oscilloscope. Not the highest performance really, but.
But this is great, you know, and I make them do the connection for the electricity with the electronics. And when they use, we have, I have what is like, it's from home, and a lot of what I use in classroom very often is my own personal material, or I steal my husband's, but don't tell him. And he's a computer engineer, electrical and computer engineer, so he knows I steal his stuff. But anyway, we have both analog and digital multimeters. And so to be able to make the connection, I'm big on hands-on and teach them the analog part before going into the digital side. And so that they understand, I want to demystify all this electronic and these computers. It's like, computers are dumb. They are smart as the programmers, you know, it's very simple. It's a box that does whatever you tell it or program it to do. And a lot of people, you know, it's so complicated that they get scared off. And
yeah, we did quickly go shopping for a magnetically deflected meter for this kit, and it just didn't work out price wise.
Yeah.
But I'm glad that you can do that for your students, and that might actually, I'm going to make that a note for the teacher's guide.
Well, a lot of CTE teacher will have multimeters, and so they'll be able to compare what is measured by the cyboscope with the electronic they have at home.
Yes.
Or in the classroom. Sorry, I say home because like I'm playing in my corner. It's like with COVID-19, I dug a hole in the corner of the pantry area that became my office.
That's so funny. You know what?
Nice.
I thought that was your school office.
No. It's just a corner. Here I have food. I never go hungry in here.
Yeah. You can just reach off screen, and on screen comes a Snickers bar.
Exactly. Well, here I have, so it's part pantry, part like supplies, art, office, school supply type thing. So it's a small den that got transformed in a pantry / supply room. And
yeah, but you have the right setup there. I can see the anti-static wristband there. Yep.
Nice. I missed that.
Yes. So
That's
she
cool.
can say, I don't have it here.
Yeah,
one of those.
well, it's because I have, my thing is on a, I don't know if I can lift up enough. I don't want to drop the resistors on it, but yeah, I have my anti-static
mat. Yeah.
Yeah.
Nice.
I got it. And the thing I've done for the cadet is I went to Amazon and I found for a decent price a huge mat. It was cheaper to buy a roll than I can cut them in smaller parts to put on the table for the cadets. So it's not exactly the same as this one, because this one is also, it allows some temperature for soldering also.
Oh.
But for them, for what they're doing, it's kind of teaching them the habits of, you know, it's electronic. You have to worry about static. And so it's a lot of what we're using is probably not that sensitive, but it's a good mindset to have. And for them to remember, you don't put your hands in a computer like that. You pull out your anti-static bracelet. And so I guess it comes from the fact that I'm a chemist, I'm a geologist and a chemist. So, and I know that when I teach chemistry in elementary school, I teach the lab like if there was highly toxic chemicals, even if they're using water and sugar or water and salt, it doesn't matter. They treat like very dangerous chemical. So they take the habits of real lab environments since the very beginning. So they do electricity where you have to treat it like you're going to get electrocuted. And you have to treat it like you're going to zap it, so that when you will be doing more advanced and more dangerous or more sensitive, working with more sensitive equipment, you will have the habit of thinking about precautions and safety. So
nice.
Yep. And yeah, that's great. Unfortunately, with the kit, we cannot go quite to all those links, but we do similar things, like testing the continuity. And then, for example, when we get to these servos, we'll be using the voltmeter to test the battery supply voltage of the servo and things like that. So yeah, wherever possible, we try to put in the real aspect of, proper procedure and electronics for, building and testing a circuit and stuff like that. I wish we could include an anti-stat mat and the other stuff.
That's too much.
but for teachers who can, that's fantastic. You said you buy rolls of that. Do you have like a rivet gun to put in the snap to or how does that work for you?
That's the easiest way of doing it, is putting a rivet in it.
Okay.
But what it's just that rivet gun, you find that at craft stores.
Yeah.
Mm-hmm.
Then from there, you just go from it, and it's a cheap way of having it. The cadet, even if they have, and I'm sorry I say cadet because I do a lot more of these technology things with the cadet than the students, sadly. But with them, they don't need to have a huge size. If they have an 8.5 by 11, that's plenty. That's more than what they need the majority of the time. Because I want them to put the electronic on it. So you can even have them draw lines, or this is where you put your components. And so that they take the habit of putting their little trays. I usually use glass trays. I don't want plastic because plastic is electrostatic. Well, glass also, but a different way anyway. But if it's a little bit, they can just put it, in these rectangles, so that because I want them to be organized. And that really helps. If you have an organized learning environment, you're gonna have an organized learning experience. What you say about colors is very important, because color coding is one way that we learn through color coding. The fact that your red is plus and your blue is minus, it's a big deal. So even though it's usually red and black, but for us, the minus, depending on the schools, the minus is always, the subtraction is always blue. So I was like, this is perfect. It's already color coded with the way we do it even in mathematics. Because our mathematics is coded in the Montessori environment. And for them to follow the flow and where it comes from and where it goes, the fact that you keep these colors really helps them follow the flow. So I'm glad that you're careful with that. I was concerned at first when I say, ooh, 4 colors of wire, how is that going to be used? And when I look at your schematic, it's like, no, you are really following the flow. You kept that structure, so that's perfect. And that's an organized way for the youth to learn what is what and to follow the flow. So now that's perfect. You're doing a great job. I'm really enjoying it. And a lot of workshops or material I use, I have to adapt it, transform it to be able to use it directly. There, a lot of yours, I don't have to, it's already done. So thank you.
Nice.
Oh, wonderful. That's the best possible news we could have hoped for. Yeah, excellent.
No, that really, really helps. So no, thank you for all the efforts and all the time you're putting into all this. Like I say, it makes my life very easy. So when I put the proposal for the electronic workshops to have like more advanced material like yours, instead of just like little secretary thing, and robotics, already they say, yeah, but what about the curriculum? The creator's like, no, I don't have to create the curriculum. It's already created. A bunch of it is Parallax and cyber.org. I'm like, no. It's like we can expand from there, but they have all the core curriculum already prepared. It's like, I don't have a lot of work. I have a lot of time to spend with my cadets. That's what we want. So no, thank you very much. Really appreciate it.
Well, thank you for the feedback. This is wonderful.
Thank you. Thank you for all the hard work.
Oh yeah, glad to be doing it. How you doing there, Thomas?
Well, I think that it's beneficial to do that exercise with the breadboards.
Good.
Yeah.
Good. Yeah.
If it's necessary to do it, then it's a good exercise in breadboards, if it's necessary.
Yeah. There are some classes where the teachers basically already know this, and they have already their favorite way, their tried and tested way of imparting it on their students. The thing that we find is that there are a number of teachers who are stepping into this, and they are learning as they go. And so for those teachers, what we did is we made that entire resource available. I realized that I did spend a lot of time on that today, but it is for the benefit of the teachers who have to learn as they go, as well as for self-schooling students. So some of the students who do this are going to be homeschool students. And wow, is that a receiver in the background? Sorry, I just got distracted.
Yeah, there's some radio Sirius equipment.
Is that like a commercial receiver?
Yeah, it's an AOR 5000.
AOR 5000?
Yeah, it's a receiver, commercial receiver. Yeah.
Okay, cool.
But Andy, the other thing is the fact that the teacher very often in some of these classes is more there as a guide. The fact that it's well presented on the website allows the student to work also at their own pace.
Good point.
So
we do the introduction at the beginning, we show them what they're going to do, they go on there, and then they're going to continue on their own, and they can use the website as a major resource because of the way it's presented. It's very and so that'll work really well for that.
yeah, about 20 years ago, I started in Parallax and one of my first trips was to Utah, and we were converting workshop places, workshop labs, and the workshop teachers into robotics. So they had only woodshop.
Like woodshop?
Yeah, woodshop, and no robotics, no electronics, no programming. And we have a lot of robotics clubs in schools, and a lot of teachers. It's just the teacher is sometimes a librarian, is just a coordinator. They usually do not have either programming no programming nor electronics backgrounds, and they need to be able to just facilitate the space, the access to the hardware. And the idea that Andy, all the documentation needs to do is to support that the students can go through that and they get all the learning. So it needs to be from ground zero, electronics and programming.
When are you going to have workshops on the P2 chip and something about how can I get the serial LCD I2C to work?
On the propeller chip, there are, if you go to the Parallax forum, actually, there's a live event every week. They have a weekly session on the propeller 2. And there are presentations there, and also there's a live discussion.
I need help for a presentation. I needed help to make this presentation. And look, I have this other P2 evaluation board that's got a problem. Okay, the pin 62 doesn't work. Okay, it's a $150 board, and the pin 62 doesn't work.
Yeah, that will have to be, that's a very different product line, different people here from the
so
Cyberbit.
Since we're getting off topic now, I'm going to stop the recording, if that's okay.
Yep.
Okay. Do you want